You guys do this because you guys are doing this warm-up. Not here, I meant on here. Come here, do this on the iPad. Thank you. You can just write it right up. Okay, guys, our warm-up problems. That second one is patterns, right? We are all about recognizing patterns for the first several weeks in Calculus 2. We're getting used to these, to this language of mathematics and all the patterns that erupt in these integrals that we're working on. That second one is a pattern, and you guys should see arc sine of x. Okay, 1 over the square root of 1 minus x squared. Arc sine of x. Yes, sir. Yes. Well, you could, but we're going to use u substitution because it's much easier with a u sub. On that first one, right, the number one easiest method in the world is u substitution. So you look to see, do I have a pattern that lets me erupt and create a u substitution? You did. Did you write on my board yet? Did you write on my iPad? You've been on my iPad? You've been on my iPad. Did you write on my iPad, Derek? Did you get an answer? Did you get a nice U sub? Oh, you did. Can you go put that up there for me? All the steps? Thank you. That first one, you're looking at a U substitution. Why? Because it's a what and a what? It's a what and a what? It's a function and a function. What was our U? What did you let U be? 16 minus x squared. Derek's going to write it out for us. U equals 16 minus x squared dx is going to be negative 2x dx. Do not lose that negative 2. Some of us will lose that negative 2, and then we'll get a wrong answer at the end, and then WebWork will spit at us bad. Don't lose your negative 2. Make sure you got your negative 2 in there. Thank you. Oh, beautiful. Du on the back end, Derek, for me. Oh. Thank you. Beautiful. And then what do you do when you have 1 over square root of u? You turn them into u to the negative 1/2. Very nice. Add 1, flip them over. That should cancel. Oh, yes. You guys got it. You guys have it. Beautiful. So we're looking at these patterns. We're seeing composition. You see composition in there, Max? Oh, you did. Yeah, do you see what you did? Good. When you added that power 1, you flip it over and make it 2 over 1. That 2 over 1 cancels with that 1/2, and then we get negative quantity 16 minus x squared raised to the 1/2 power plus c, because it's an antiderivative or an indefinite integral. So we throw a plus c at the end. Derek, thank you for writing that up for me. Thanks, Brandon, for writing the arc sine of x up for me. Any questions? Okay. So just some housekeeping notes right here. And lots of trig substitution. So with that in mind, what is the problem if I have an integral that looks like this then? What is the problem if I encounter an integral that has this pattern? The square root of 16 minus x squared all over x. Yeah, James, what's my problem?
My function is that a function is my 16 minus x squared, which ends me up with an x. But I need a 1 over x, and I don't have a way of getting that.
I couldn't have said it any better. In our integral, we have 1 over x. But when we do a u substitution, we wind up with x dx, 2x dx. And we can't do that. There's a problem because this here, and let me just write this out, this x is in the bottom. And so if I really was going to look at that, this is actually 1 over x times the square root of 16 minus x squared dx, right? And that 1 over x is the problem. So we can't use u sub, and if we can't use u substitution, so no u sub, that means we need another method. That method of which is going to be what we call trigonometric substitution. Trigonometric substitution, you're going to be looking for those patterns we talked about last time, which is Pythagorean formula. A squared minus b squared, or c squared minus b squared, or x squared plus a squared. The squares, squared minus squared, or squared plus squared, especially inside a square root. That should signify to us trigonometric substitution. One more quick warm-up here, because we did this last time, but I want to do it one more time, all right? Let's practice our right triangle trig, okay? A couple people, I think, might have missed last time, but this is always good to get it going here. Practice our right triangle trig. So let's say we have a triangle theta. I want to label all sides of the triangle in terms of x. So one more warm-up problem. Label all sides of this triangle in terms of x, given that x equals, and we did not get to do tangent yet, so let's do x equals, let's say 8 tangent theta. So let's say x is 8 tangent theta. I want to label all sides of my triangle in terms of x. We did some of these last time on Wednesday before we left class. I want you to do it one more time. SOHCAHTOA, right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent's opposite over adjacent. First step being maybe just to remind ourselves from last time, maybe you want to rewrite it as a ratio since tangent, sine, cosine, when it's in terms of right triangles are ratios, right? So that's your warm-up. I mean, there's your thinking, there's your hints, and I'm going to take a little break and let you guys do that. One more thing. Label all sides of the triangle in terms of x, but then I want you to find cosine of x, cosine of theta, and sine of 2 theta in terms of x. All right, sorry about that. So label all the sides and then find cosine of theta and sine of 2 theta. Pointing that out, Caitlin, and thank you for asking James 1000%, right? Because you have a single theta, but you need a double theta, and the single theta doesn't match with the double theta, so I'll just give you as a hint that sine of 2 theta, double angle identity. Anybody remember what sine of 2 theta is? It's 2 sine theta cosine theta. That's on your formula sheet, I believe. Sine of 2 theta is 2 sine theta cosine sides. Yeah. All the sides here. And here's a pen, and you can change colors if you want. You can use black. What color you want? Black, blue, what color? You can just change it. Here you go. Blue it is. Alrighty, so label all sides in terms of x. Label all sides in terms of x. So x over 8 is tangent theta. Oh, did it work? Yeah, hit this one more time. See if that works. Okay, good. It should go. Yep, now. Oh, you can hit it back again now. There you go. There. Good. 8 squared, right? 8 squared.
Is it?
It is.
So I got x squared plus 64. Can I simplify both of them right now?
No, you can't. So I want
okay.
square root of x squared plus 64. You did it perfect on your paper. I liked what you had on your paper. 1000% I liked what you had on your paper. You don't like yours? Why don't you like yours? Oh, because you don't have anything on your triangle. That's why. So tangent is x over 8, right? So that's x,
Yeah, I know.
and that's 8.
Yeah, I know.
Oh, you did it. Oh, okay. And so then what's the hypotenuse? So x over 8. What's the hypotenuse? But I wanted x's like this. I want to make it. Hang on.
Am I doing this wrong?
Get rid of your sine theta for me. Hang on. Get rid of sine theta for me for a second. You had the cosine theta right.
Yeah.
Hang on one sec. Let's see. So x over 8 is tangent, and then you did a squared plus b squared is c squared, and you got that side. You're perfect.
Yeah.
And then for cosine, you did it correctly, right?
Yeah.
Well, okay. X squared plus 64.
Yeah.
Okay. So give me your cosine theta. Write your cosine theta down. So cosine theta is going to be 8 adjacent over, you did it perfect, 8 over, square root of x squared plus 64. Good. Perfect. All the way. The square root goes all the way. Can you put the square root all the way? Good. Okay, now you want sine of 2 theta, which you said is 2 sine theta cosine theta, right? So write down for me 2 sine theta cosine theta. 2 sine. Oh yeah, you had it right. You just have to write x squared plus 64, not x plus 8. Yeah. Good. Equals. Go ahead. Good. You got it. Guys, are you guys getting the same thing he's getting? Does everybody get square root of x squared plus 64?
What am I doing?
On that triangle hypotenuse. And then you're getting sines and cosines.
This is so
right?
stupid.
Everybody's getting this. Is everybody getting this? Get this? Two theta is 2 sine theta cosine theta. 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 How are you? Everybody's good.
Someone retire me now.
Nice. Thank you, Ben. Thank you, Ben. That is beautiful. That is beautiful. It's been a long week, huh? So that means, thank you for that drum roll. I'm glad about that. So what do we do if we can't do U substitution? We do something called trigonometric substitution. You're going to start saying, if I see Pythagorean identity, I want to do trig substitution. That right triangle practice we did is integral to it, but let's go back and let's talk about what is a trigonometric substitution. Alrighty, I'm going to take some notes here. I got a big box. If you're following along, all these are on Canvas. All these notes are on Canvas, okay? So let's talk trig substitutions. So if you have an integral, and our patterns, right? It's all about patterns, guys, right? If your pattern does not have U sub, then you're going to look for, and it involves this Pythagorean identity, it's going to be one of 3 forms. So, number 1 is right here, the pattern. So, right here, we're going to look for one of 3 patterns. Your first pattern will be of the form a squared minus x squared, where a is a real number, okay? So you're looking for a squared minus x squared, where a is a real number. For example, 16 minus x squared. 25 minus x squared in a square root. Could be 3 minus x squared, doesn't matter, but a squared minus x squared is the pattern you look for. If you see a squared minus x squared, the substitution you're going to make, so you look for a pattern and you make a substitution. The substitution that you will make based on that pattern is going to be, the substitution that you make for a squared minus x squared is going to be x equals a sine theta. Now we'll talk about why, and we'll talk about the restriction on it afterwards. So let me just put a third column here that we'll talk about, which is restriction. We'll talk about why we have a restriction, but that's after we actually get our brains going and talking about where this all comes from. So right now, all I'm going to tell you is if you see the pattern square root of a squared minus x squared, where a is a real number, you will make the substitution x equals a sine theta, okay? If you see the pattern square root of a squared plus x squared, which by commutative property allows us to say that's the same thing as x squared plus a squared, right? When you add 2 numbers up, you can add them in any order, right? Or objects up, you can add them in any order. Again, a is an element of the real numbers. The substitution we're going to make is x equals a tan theta. X equals a tangent theta. And the last pattern, not to be confused with the first pattern, is square root of x squared minus a squared, where a is an element of the real numbers again, okay? And we're assuming here we stay in the real world, by the way, guys, with all of our restrictions, okay? Which is why I'll tell you a little bit about our restrictions when we make some trig substitutions. So we're assuming, right, that we've got square roots of positive things going on, okay? The substitution we're going to make on that guy is going to be x equals a secant theta. And if you think about it, we have seen kind of these patterns before. In fact, one of our warm-up integrals was the square root of 1 over the square root of 1 minus x squared. In this case, a is just 1, right? Because 1 squared, a squared. But notice I fall in the first category, and what is the antiderivative of 1 over the square root? X is this is the arc sine of x. Do you see patterns? Do you see some patterns that are going on? We're making a substitution with sine. Some patterns are going on. Remember, what's the antiderivative of 1 over 1 plus x squared from Calc 1? It's the arctangent. Do you see that pattern? Do you see that pattern of how we're going to make this substitution? There's some patterns going on. Same thing with secant squared. X first. 1 over x times the square root of x squared minus 1 is arcsecant. Okay? There's a lot of patterns and beauty that go on with this kind of trigonometric substitution. All right? But I like to point those out. Substitution is my favorite method. We'll talk about the restrictions in a minute after we practice a couple of these problems. Wait, but I didn't do this one. Here we go. Are you ready? Problem number 1. All right. Like I said, trig substitution is my favorite trigonometric integration not trigonometric, but integration technique. I love them because you really have to use your brain. Well, not do you have to use your brain, but I just love them. There's so many steps, and they're so cool, and I think you guys will love them too. Some students really come to love them. So here we go. All righty, guys, here we go. We've got the antiderivative of 1 over x squared times the square root of 16 minus x squared dx. Okay. So what I want you to do, again, pattern recognition. Why can we not use a u substitution on this? Because if we let u be the inside piece, the derivative, what would u be? 16 minus x squared. So the derivative would be negative 2x dx. There's no x dx on the top. Beautiful. All right, Tim, are you ready?
Yeah.
So what's my substitution? Looking at my notes that you just took, which pattern are we in? Are we in a squared minus x squared plus a squared, x squared minus a? Which pattern are we in? Which pattern? A squared minus x squared. Do you guys all see? No, you don't, because these lights are not good. Because these lights are let's dim it a little bit so we don't have too much glare. Are you guys okay? Can you see? Everybody sees that our pattern is, just like Tim said, we got an a squared minus x squared. Ooh, undo that. So, okay, so we have an a squared minus x squared in here, right? A squared minus x squared. So what is the substitution, Tim, that I want to make? X equals,
1 over x squared.
hang on a second, look at the notes, hang on a sec, look at my box for a second. Yeah, I want to say, so x equals, go ahead, a sine theta. Now what's a?
16.
Nope, what's a? 4. So what am I going to say? X equals 4 sine theta. Thank you. Do you guys see what we just went through? Our process. We have that. No, we don't see it. You guys see it? A squared minus x squared. You see it's a number squared minus x squared. And our pattern says, look back in your notes, it says make x equal a sine theta, but a has to be 4 to get you 16. Are we all good? Beautiful. So we are going to substitute everywhere we see an x, we're going to put 4 sine theta. But we also have to deal with that dx part, okay? So make sure right away we also take a derivative with respect to x. I will tell you, even the best students, we constantly, I have done it too, forget that dx. Forget to plug that dx in, and then you get a really messy mess thing. I wish I told my other class I had a poop emoji right here. I would put a poop emoji right here. This gets really messy if you don't take the derivative. You get a really messy thing happening. So right there, make sure you somehow notate that this is something that people often make a mistake with. So I'll just put a little poop emoji here. Happy, not happy, but poop emoji. Make sure you do this, okay? Make sure you do this. No, my daughter would be better. She's good with those things. I'm not good with those things. Here we go. Derivative, dx, derivative of sine. Maddie, you want to help me out? Is 4 cosine theta d theta. Awesome. And so, that's our thinking box. We are going to make that substitution. Alrighty. So everywhere you see an x, okay, this new integration technique, everywhere you see an x, you're going to replace with 4 sine theta. And everywhere you see dx, which is one place, you're going to put 4 cosine d theta. And let's see what happens as we do that. Alrighty, so in place of x, we're putting 4 sine theta. And then it gets a power 2 on it, right? Make sure yours is matching mine. Sometimes if you color coordinate it too, it helps. So like identify this is an X and this is an X. So those are the places I have to substitute. And then the other one is a DX. So I have to make sure I remember to do my DX at the back end. Sometimes color coordination helps. Up to you. So then you get a square root of 16 minus, and then you're putting 4 sine theta in for X again. And dx is 4 cosine theta d theta. So if we're listing out steps, step number 1 is pattern recognition, right? We want to see the pattern, what's happening. Step 2 is make the appropriate trig substitution. Step 3 is make sure you take dx. Step 4 is now to plug things in. But now, what do? We need to simplify underneath this square root. And in fact, 4 sine theta all squared is just 16 sine squared theta. So let me just write it out like that. And I'm also going to put this 4 cosine theta d theta, well, the 4 cosine theta on the top. Okay, because it might get to cancel with things. So I'm just going to put it right on top. So I have 16 sine squared theta. You guys all get that, right? And then underneath you have 16 minus 16 sine squared theta. Now, why can we not take the square root of 16 and the square root is, why can we not square root both of those? Gwen? Because it's subtraction. Let me give you an example here. Sometimes when I put it with numbers, it makes more sense because people are like, okay, well, so what if I had this going on? What if I have a square root of, let's say, 25 minus 16? Well, if I could square root each part, that would equal 5 minus 4, which is 1. But the problem is 25 minus 16 is actually 9, right? And so that's not true, right? That is not true. But if I do have something like 25 times 16, and I have a product going on, then I can take the square root of each part. So this must be 400 if I multiply 25 times 16. So if I have a product under a square root, I can take the square root of each factor underneath. But if I have a minus or a plus, I cannot take the square root of each part. Do you guys see that? So because I cannot square root the 16 and I cannot square root the 16 sine squared, I have to instead change it into a product. How do I take a polynomial and turn it into a product? Or an expression that's like a polynomial. It's not really a polynomial, but it's like a polynomial. Gwen?
Can you pull out a 16?
Yeah, let's pull out that 16. Factor, right? Factor. Write it as 2 factors. So let's write that as 2 factors. So that's going to give us, let's see what Gwen says. Gwen says, let's pull out a 16. So that's going to give me 16 sine squared on the bottom. And then I pull out a 16, and I'm left with 1 minus sine squared. Ha ha, ha ha, ha 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 ha. Okay, guys, 1 minus sine squared. Hunter's smiling. Why are you smiling?
1 minus sine squared is...
Because 1 minus sine squared is cosine squared. Remember that tattoo? That tattoo that you guys have on your arm, sine squared plus cosine squared is 1, right? 1 minus sine squared is cosine squared. That good old Pythagorean identity is going to put us cosine squared. So that gives us underneath that square root a product. It gives us a product of 16 times cosine squared. And once I have a product, are you with me? Benner, you see that? Once you have a product, now you can take the square root of both pieces, right? Provided, well, hang on. So let's write this out. Go slow, Tina. So, are we all good? 4 cosine thetas on top so far. 16 sine squared theta is outside. Now, because I have a product right here, I can simplify this square root down. Square root of 16 is 4. Square root of cosine squared is cosine of theta, provided cosine of theta is greater than or equal to 0, right? I'll just put this little restriction here because we'll go back to our chart because I wrote restriction down. I said something about that. We'll put that restriction in afterwards. But do you guys see cosine theta has to be positive? Otherwise, when it comes out opposite of a square root. So a square root of x squared is positive provided the thing inside was positive to start with. Okay, I don't know if that makes sense or not, but that's true. All right, how are you, Tim? Good? Did you cancel some things out for me and finish this integral? Did you guys finish this integral? Once you do that factoring and you get the thing out of the square root, your problem kind of goes away, doesn't it? Now, do you see? Oh, yeah, I see a couple smiles. I see a couple people are like, oh my God, Tina, I can do this integral now. Zach, what are you canceling here? 4 cosine. You're canceling my 4 cosine theta. I'm canceling my 4 cosine theta. When you cancel that 4 cosine theta, what are you left with? 1 over 16 times the integral of 1 over sine squared theta d theta. All righty. What is that, Ethan? Do you know that trig? What is that trig identity? 1 over sine is cosecant, so 1 over sine squared is cosecant squared. Oh yeah. 1/16 times the antiderivative of cosecant squared d theta. Oh yeah, Zach, help me out here. What's the antiderivative of cosecant squared?
Negative cosecant cotangent.
Close, very close. Just negative cotangent. Just negative cotangent. Is it just negative cotangent? Derivative cotangent is cosecant squared? Oh, did I do it wrong? I said derivative. I said derivative of cosecant squared, didn't I? I think I did. I think I said derivative. I went to antiderivative of cosecant squared. I think I said derivative. Antiderivative of cosecant squared is just negative cotangent. I'm sorry if I said the derivative of cosecant squared. Antiderivative of cosecant squared is negative cotangent. Absolutely. You guys practiced that for breakfast, right? You guys know these. You're quizzing each other. Did we not say do that from day one, right? What's the derivative of tangent? Secant squared. Derivative of cosecant. Cosecant cotangent. Derivative of cotangent. Negative cosecant cotangent. Negative. You guys good? Are we good? Okay, are we done with the problem? Are we happy? Are we done with the problem, John? Are we? Are you sure about that? Are we done with the problem, Dylan? Probably? Hang on, guys. Put your thinking caps on. Allie, why not?
Because you didn't substitute x back there.
Because we started with x's and we finished with thetas, and that's not good. We need to go back and turn it into x's. Okay, guys? We need to go back and turn it into x's. Put your thinking cap on. Go back to the very beginning where we actually made our initial relationship between x and theta, which is x is 4 sine theta. Are you with me? Hello. X is 4 sine theta. That means x over 4 is sine theta. What do you think would be helpful here? A right triangle. Oh, yes. Absolutely a right triangle would be helpful here. We're looking for cotangent theta. We've got x over 4 is sine theta. Are you with me? So now you're getting a right triangle. It's a good thought. It's going to help us go backwards. It's absolutely going to help us go backwards. We're not done, right? We got thetas to deal with. Good. What side is that? Yeah. I know, it's hard when your teacher just calls on you, does it not, Zach? When I call on you, you just blank. Like everything just goes blank. It's like, It's like when sometimes you ask me a question and I'm like, oh my God, I didn't think of that. I don't even know how to answer that one. Absolutely. What'd you get? X is opposite over hypotenuse, right? So katoa. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent's opposite over adjacent. Sine is opposite over hypotenuse. You guys are labeling this big side x, right? Hypotenuse 4. And you're using good old Pythagorean theorem like we did. We practiced like 3 or 4 of these, right? What'd you get down here, James? What'd you get? 16 minus x squared. Hello, beautiful 16 minus x squared. You guys should recognize that pattern. 16 minus x squared. It actually came from the first integral we started with. that's a clue that you did it correctly. If you get this side to match the side that was originally in your integral, then that's a clue that you're doing it well. Does that make sense to everybody? Okay, all right, Gavin and Max, I'll get you team-wise here. Can you give me the cotangent of theta based on this triangle then? What's it going to be? Cotangent of theta. Okay. It is absolutely the square root of 16 minus x squared divided by x. Thank you guys for participating. I truly believe that to become experts in Calculus 2 or any mathematics course, you have to speak it. You have to practice talking it out and thinking it out and reading it and speaking it. That's how you get really good with it. Okay. I thank you. Negative 1 over 16 times the square root of 16 minus x squared over x plus c. Beautiful. How are you guys? Good? How are you guys? What do you think of trig sub? It's kind of fun. All right, before we go on and do any more, I want to go back and talk about those restrictions because I want to be rigorous about my mathematics. Oh, hang on. Before I talk about being rigorous, any questions? Let's talk about restrictions, okay? I said that in order for this to all work, we needed cosine to be positive. So let's go back to our chart and talk about restrictions really quick. What we notice when we make this x equals a sine theta is you wind up with an a squared minus a squared sine squared. And if you factored out an a squared, you're left with 1 minus sine squared. So what happens is, through this substitution, we wind up with 1 minus sine squared, and we go and we simplify down to get cosine squared, but it's in a square root. Are you guys good? All good? So we need, if we're in a square root, we really want cosine to be positive. So we really want cosine to be positive to make the square root of cosine squared. And therefore, what angles do I need for cosine to be positive? What quadrants do I need to be for my cosine to be positive if I'm talking about a unit circle? You know what I mean? What quadrants? From my Hunter. The first and the fourth. Or in other words, so I want to be up here or down here. So in other words, I want theta to range in between negative pi over 2 and plus pi over 2. This restriction, you're not going to need it, okay? But I, as a mathematician, want to have this rigor to say, this is what's happening behind the scenes. Square root of cosine squared will be cosine provided cosine's positive. Where is cosine positive? It's in these two quadrants. It's good to talk through this and understand this because you guys are engineers, actuarial science. You need to have these thinking skills to work backwards. If I put a tangent theta into my square root, so then I have a squared plus, or a squared tan squared plus a squared. Do you guys see what I mean? Like underneath my square root, I'd have a squared tan squared plus a squared after I make that substitution. I factor out an a squared, and I'm left with tangent squared plus 1. What can I replace tangent squared plus 1 with? Secant squared, right? Secant squared, because that's that Pythagorean identity that we talked about last time. Secant squared, right? And if I'm taking a square root of that, again, I would need secant theta to be positive. I would want secant theta to be positive. It can't be 1. It can't be 0. Okay, secant can't be 0. Okay, so I want secant to be positive. And that's equivalent to saying, where is secant positive? Well, that's the same place as where cosine is positive, because secant is 1 over cosine. Got it, Derek? Yep. So give me a restriction. Where is that true? Between? Negative. Yep, 2. Pi over 2, beautiful. Put it open because cosine, we don't want cosine to be 0 because then we have 1 over 0 and secant's undefined there. So that would be the restriction on this one. And this bottom one here, if I plug in a secant theta, I don't know if you guys can look ahead. If you plug in a secant theta, you're getting a squared secant squared minus a squared. And so what's going to happen is you're going to be able to factor out an a squared and get secant squared minus 1. Secant squared minus 1 is just, Zach, what is that? Is tangent squared? Yeah? Tangent squared? Okay. And so again, we're going to follow that same rule that, okay, in the cases where it's inside a square root, we need to make sure that tangent is positive. Ha. Where is tangent positive? The first quadrant and the third quadrant, right? Okay, good. First and third. Okay, can you give me angles up there? Gavin, you want to try the angles up there? So we start at 0 and we go to what? Erase that. Oh, quadrant 1. Sorry, you can't see it. Sorry. Thank you for telling me. So we want up in first quadrant. So we want 0. Yep, thank you. 0 to be, hang on a second. 0 to be less than or equal to theta to be less than pi over 2. Tangent's undefined at pi over 2. So, or if we're down in the other quadrant, we would want pi to be less than or equal to theta less than 3 pi over 2. Again, this is not going to impact you as you're doing your trigonometric substitutions, but it's important to recognize the mathematics that's going on behind the scenes to make everything fall out nicely for us, okay? So that's why I like to talk about it. I like to talk about it just because it's trig, and anytime we can talk about trig, it gets our brains thinking more trigonometry, okay? Okay, so let me pause. Too abstract too fast. It might have gotten too abstract too fast. Your goal right now is to get this method down and to look for those patterns and see what's happening, okay? Are you ready? Here's your first pattern. Here's your first problem. Antiderivative of 1 over the square root of 4 plus x squared dx. Antiderivative of 1 over the square root of 4 plus x squared dx. God, I love trig substitutions. I really do. I really love this mathematics. It's so beautiful. Can't use u sub because there's no x on top, right? Can't use u sub. Maddie, what are you thinking? Which one? Which pattern? The tangent. You're thinking tangent. Your a value is going to be 2. Beautiful. Beautiful. You guys are making out some substitutions. Absolutely. You're looking for the tangent one. Your a value is 2. Beautiful. I'm going to wander. That way I can just look over what everybody's doing and you can ask questions. Do not lose your d thetas and dx's. So Maddie said that's a tangent pattern. So she sees a squared plus x squared. That's x equals a tan theta. So we're going to make the substitution. X equals 2 tangent theta. And dx is 2 secant squared theta d theta. And so when you guys are back substituting, in place of dx, you're putting 2 secant squared theta d theta, and in place of x, you're putting 2 tangent theta. And so really, the integral that you have inside is 2 secant squared theta. Guys, catch me. Catch me if I'm making any mistakes. 4 plus 4 tan squared is what I'm getting underneath my integral. I cannot take a square root of each part because of that plus, so I have to turn it into a product, which means I have to factor. So I have to take out a factor of 4. Did you take out a factor of 4? Zach, did you get the factor of 4 coming out? Oh, both Zachs. Yeah. Good. So you're pulling out a factor of 4 right here. And you're left with 1 plus tangent squared, which you're going to replace with secant squared. Thank you, Anthony. I heard that. I don't know who did that. You or Chris. Did somebody say secant squared?
I didn't.
Oh, yeah. I thought you did. I thought for sure I heard that. Maybe Garrett gave me secant squared. 4 secant squared theta. So you're taking now, once you get that product, right? Once you get that product, now you can square root each part. Okay. So, Maddie, you're looking at it. I can see. I think you got this far. Maddie, check me and make sure I'm good here. Did you get 2 secant theta when you did that? And then you canceled down? And what'd you get an integral of? Just secant. Oh. Are patterns going on in your head? We did this last time, didn't we? We did this on Wednesday. I know we did this Wednesday. I think I did say, I think I'll give this to you on your cheat sheet. Antiderivative of secant. Look back in your notes if you don't work too guys. Yeah, James.
Tangent squared.
Close. You're going other way. The derivative of tangent is secant squared. You see what I'm saying? That you're very close. And the antiderivative of secant tangent is secant. Why don't you give it to me? It is gross. Remember, not gross. I don't know if I would say it's gross, but it's involved, isn't it? What is it? Help me out, James. What is it? I love, though, that you got some patterns going in your head. That you thought, oh, maybe it's tangent. I love that you guys have patterns in your head. I do love that. I do love that. Antiderivative of secant, we multiplied top and bottom by secant plus tangent. Is that what you had, Gavin? Did you get the natural log of the absolute value of secant plus tangent? Beautiful. Eva was not here. Logan is going to give her the notes to show her. Did you get those? Did you get those? Yes. Okay, awesome, 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 awesome. We have thetas. We need to go back and get x's. Did you get me a right triangle? Brandon, you got me a right triangle. Oh, you do. You're all the way back. Give me... Give me tangent. Good. Roll it back up there. You didn't answer all the way down. Oh, yes, you did. Yes, 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 yes. Yes, yes, yes. Yes, yes, yes. All right. You guys are saying, okay, I know I have to go back and get x's. A bunch of you guys already have your triangle. Nice, nice, nice. Here we go. So if I have x over 2 is tan theta, opposite over hypotenuse gives me, hang on, I did that wrong. Erase, 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 erase. Hang on, erase, erase. I did that wrong. I'm going too fast. Going too fast. Going too fast. Hang on, let's try that again. Tangent is opposite over adjacent. That makes this guy x squared plus a squared or x squared plus 4. And that matches the thing I have in my original integral. So I know I'm all good. Alrighty. Work me back. Work me back. Gavin, give me secant of theta. What'd you get? Oh, no worries, no worries, no worries, no worries. Garrett, did you get one yet? Or are you still writing it down? Still working? Robert, give me secant. Over 2, square root of x squared plus 4 over 2, hypotenuse over adjacent, plus tangent. Caitlin will give me x over 2, tangent x over 2, plus c. Now, if you do this and plug this into Wolfram Alpha or Desmos to check your work or anything like that, chances are you might see this happening if you plug it into some kind of like Symbolab, or I don't even know if Symbolab does integrals. I don't know all that technology stuff, but you might see something like this going on. And the reason is because logarithm rules allow you to put x squared plus 4 plus x. You could put that over a common denominator of 2. And then we have these logarithm rules that say if you have a quotient, it's the natural log of the top minus the natural log of the bottom. And so that would give you the natural log of absolute value of x squared plus 4 plus x minus the natural log of 2 plus c. And those two could get absorbed into a new constant. So what I'm trying to say, the moral of the story is, when we do our trigonometric substitutions, we get to this step here. I am fine if you stop there, but if you're checking your work with an online program to check your work, they might give you something slightly different, and if so, it might be due to this logarithm rules and properties that they're using. Does that make sense to everybody? Just so you know. But this is my nice answer. I am happy. How are you guys feeling with that second one? Was that one okay? A little smaller, shorter than the first one? What's the most challenging step? Most challenging step? All of it? What do you think? Recognizing the pattern at the beginning? Knowing what to do? How about finding that trig integral? I think that might be one of the most difficult parts of this whole thing. But it's so fun. Are you ready for another one? Are you ready for some more fun? Are you guys ready? Yes. Here we go. You can see the peak down the bottom. Here we go. Are we ready? Here we go. I am taking the antiderivative of... Wait, slow down, Tina. I didn't ask questions. Hang on. Any questions? Right here, question? Brandon, question? No? Eva, question? We're good? Logan, question? Everybody's good? John, good? Vincent, how are ya? You are like 180 degrees from me. Okay. Any questions? Are you okay? Okay. I like that. I feel fine. Absolutely. There's got to be a song with that, right? I feel fine. There's got to be a song. Antiderivative of the square root of x squared minus 49 over x dx. I like those smiles. This is fun. No, I don't like the crowds. We like doing substitutions, other than, as Allie says and points out, it's a page long. But if you go really slow, there's some beautiful mathematics that falls out. Really, there's some beautiful mathematics that falls out. I'm going to wander, guys. Started. I think everybody's got us started okay. I think you guys are all recognizing your pattern. So you guys are recognizing x squared minus a squared and x equals 7 secant theta and dx is 7 derivative. Oh, Hannah, what'd you get for your derivative of secant? Yes, thank you. Yes. I am going to underline again that, remember that derivative piece. Do not lose. I'm going to say it again and again and again. Don't lose your derivatives. Because if you lose your derivatives, then your integral just falls apart on you. Okay? Do not lose your derivative piece as you're doing this. And yes, you can cancel those 7 secant thetas right away. Yeah. Yes, you can. I'll be right there. Let me come right up there. With the alpha. You guys are enjoying this a little bit. You have to say it's a little fun. It's a little fun. Little bit. Secant squared minus 1. Are you guys seeing the secant squared minus 1 and replacing it with tangent squared, right? You're using good old Pythagorean identity, replacing secant squared minus 1 with tangent squared. So you guys are getting the integral of the square root of 49, tangent squared. I canceled the 7 secant theta at the first step just because it made it simpler. And so let me see if you guys are getting the integral that I'm getting. Are you guys getting down to 7 tangent squared of theta d theta? And this is those patterns, James, right? I don't know an antiderivative of tangent squared. I know an antiderivative of secant squared. So did you guys change this? Yeah. And what is tangent squared? It's what? It's secant squared minus 1. So you guys say, okay, I can't take the antiderivative of tangent squared, but I can take the antiderivative of secant squared. And since tangent squared is secant squared minus 1, I put the 7 out front. Antiderivative of secant squared is? Antiderivative of secant squared is, Acacia, you know what that is? And tangent, right? Tangent. Antiderivative of 1. Theta. Theta, because we're integrating with respect to theta. When you take the antiderivative of 1, it becomes theta. So really, my answer here is going to be 7 tangent theta minus 7 theta plus c. And don't forget, we have to go back and turn it into x's. You never stop thinking on these problems. They're fun. They're fun. Let's see. Did you label this x and this 7? And then this becomes x squared minus 49. Where are you getting stuck, Brandon? Are you getting stuck or are you good? What is the tangent? Anthony, you got the tangent?
Square root of x squared minus 49 over 7.
Okay, beautiful. How about 7 theta? What is theta? Glenn. You do, or arc functions, right? Theta is an angle. Theta is an angle. Secant, sine, cosine, those are numbers. Those are quotients and ratios. So to get theta, we want to take the arc secant of x over 7. Theta is the angle whose secant is x over 7. Theta is the angle. And so anytime you see thetas, you're thinking inverses or arc secants. So that, well, arc secant, arc sine. Our problem has an arc secant in it because we have a secant in it. It is the angle whose secant is x over 7. So you could write that as the arc secant or as secant to the negative 1, the inverse secant function. Yeah, James.
Could that also be the arc cosine of 7 over x?
It could also be the arc cosine of 7 over x. Other questions? How are you? Is it bringing you a little bit of fun? A little bit of puzzles? A little bit of joy? Questions? A lot of what? Excitement? Oh, I like that. A lot of excitement. I am going to give you a survey by the end of this semester, and I want to know what brings you joy in math. I do. I want to know, what is it? So I'm just telling you ahead of time. What is it that brings joy in math? Maybe nothing, but something. There has to be a little spark. Whatever it is. Maybe it's using alphas, thetas, maybe it's trace, maybe it's getting an A on a test. I don't know. So by the end of the semester, I want to know what brings you a little bit of joy in math. How are you? Ready for the last problem? We're going to do one more. I think we're going to do one more. Are you ready? I think we have time for one more. Are we ready? Any questions? Here we go. Last one. And it looks so innocent. What do we got? We got a composition. Square root of 1 minus x squared. The problem is we can't use u sub. The other problem is, even though this is half a circle, right? Square root of 1 minus x squared, if you have y equals square root of 1 minus x squared, you're getting half a circle. I don't have limits. I don't have limits on here, so it's an indefinite integral. So what do you see? Can't use u sub, but it's got that good old a squared minus b squared, right? Or what a squared minus x squared. We've got a pattern. So we can use a trigonometric substitution on this innocent integral. Yes, sir. I don't know, you want me to put them on, or do you want to keep them? Do you want to just memorize them for me? I am going to give them to you.
What?
So let's say I give them to you.
Trying to jeopardize everything.
I'll tell you what, you may not have calculators on my test, okay? No calculators, but I will give you a formula sheet, okay? I want you guys by hand to do mathematics, but I know how you blank out sometimes. I have blanked out on a test. I literally took a test once and walked out with nothing on my paper because it was just one of those days. So I will give you a formula sheet. Okay, so for those of us that might breathe a little heavy, I'm in school again. I know. I see that test and my blood pressure goes up. Like it really does. So I will give you a formula sheet and we'll have these on it. That formula sheet I will make sure is posted on Canvas. It is on Canvas right now, but I'll identify it so you guys can find it and know what I'm giving you. Yes, sir. Oh, opposite over a basic. Oh yeah, they would cancel. You could do it that way. 1,000%. No, you can't do that. 1,000%. Or you could do sequence -1. Yes. Yep.
It's like is that what you're doing? Yeah. It's like the power reduction. Yeah. So
How are you? Oh yeah. Oh yeah. Oh yeah. You're getting to an integral of cosine squared. Ooh, even power of cosines, right? What are we thinking? Max, what are you thinking? What are you thinking, Garrett? Cosine squared. Antiderivative of cosine squared. Brandon, what are you thinking? Antiderivative of cosine squared. Power reduction. Power reduction. Yes, yes, yes. It's all about the patterns, right, guys? We're looking, we're thinking. Okay, so let's see. So this is going to be, see if you guys are doing this. You're making x to be 1 sine theta. Dx is going to be cosine theta. You guys are getting cosine theta times cosine theta or cosine squared theta. And then you're saying even power of cosine squared needs power reduction formula. Wait, what was that formula? Hunter, give me that formula again. Cosine squared is? Thank you. 1/2, 1 plus cosine of 2 theta. Absolutely. Let's fix that.
This is right.
Antiderivative, you got a d theta. You guys are remembering that d theta at the back end because when you take the antiderivative of 1, you're getting theta. Okay? Antiderivative of cosine 2 theta is going to be 1/2 sine 2 theta. You got an answer for me? Good. And then you get sine 2 theta in your answer? So let's see. Are you guys getting 1/2 theta plus 1/2 times 1/2 sine 2 theta. Is that right? Did we do that right? Right? I can distribute that half if I want to. Be real careful, right? Then you're like, oh yeah, Maddie's like, oh yeah, Tina, hang on. My triangle's only got theta, so if I have to have a 2 theta in there, I have to use my double angle identity. I saw it in your eyes. I knew you were doing that. Tim, what'd you do? Did you get me an answer?
I don't know where to go anymore.
Wait, hey, slow down. Did you get your triangle?
Yeah.
Okay. Now, theta is what? Theta is an angle, so we represent it with arc. Did you get the arc sign?
I don't know.
Ah. So x over 1 is...
No, it is just... Yeah.
Yeah, so theta is the arc sign. You got it? So that's arc sign of x over 1. Yep. X over 1 or just x. Yep. What was sine 2 theta? What's sine 2 theta? 2 sine theta cosine theta? So that's times 2 times the sine of theta. What's the sine of theta? Sine of theta is x over 1, right?
Yeah.
And then cosine of theta is square root 1 minus x squared over 1. Okay, so let's clean this up. I'm getting 1/2 arc sine of x plus x over 2 times the square root of 1 minus x squared plus c. Did I get that? Is that what you got? Or 1/2 x times the square root of 1 minus x squared plus c? How are we? How are we feeling? How are we? Bad? No, we're good. We're so happy. 1000% happy.
That's what's good.
Who's got questions? Who's got questions? Record this part so somebody. Yes, sir. Yeah, we're fixing that 5 squared. That'll be a 5 squared. There's an extra 5.
I don't know, bro. I don't know what that is.
What's dx? What's dx? 5 tangent theta. Yeah.
Now it's...
Who's got questions? Who's got questions? Who's got questions?
So you have sine and then
It's good, bro. It's good, bro. What about you, sir?
so then those will cancel out. So you're just like
I tend to separate them,
sine to the eighth.
keep them separate from my sequence.
Yep, stupid kids.
All
No, yeah, but you have.
Oh, that's an issue.
No, that's an F.
I got 10, 5, well, we can put 5 on
These
5,
ones,
and then you have 5, 7, 5, 9, then the rest is 1 and 5. You double it because you have to put it on. And then you put it on.
Tango, you couldn't even get past the second step.
So I would keep it 7. Be careful when writing this 5
I tapped out like 3 times. No one wrote it down.
Nope, I guess it's like the eighth.
No one wrote it down.
Just a little bigger. Thank you, James. Thank you, James. How are you guys? So I'm going to tell you, I give you points, okay? Remember, I do partial credit because these problems are so long and it's so easy to make a small mistake. So if you make a small mistake, like you lose a 5, if I don't give partial credit, then I would be marking the whole problem wrong. I don't want that. I want to see progress. I want to see that you can recognize, oh, this is a problem that needs trigonometric substitution. Oh, what is the substitution that needs to be put in there? I want to see critical thinking all the way along, okay? So you will get points for showing me that you recognize this is a trig substitution and that you need the proper trig substitutions. You will get points, right, as you bring it over and stick it in the correct places. So if you forget to put 5 secant theta in the bottom and raise it all to the 10th, well, your problem's going to be wrong. But if you can do everything else to a certain point, then I get partial. Does that make sense to everybody? So put down all of your steps. Plug everything in where it goes. Don't lose your d theta with your dx. Make sure it gets put in. And when you have these big numbers, like 5 to the 7th and 5 to the 10th, think of the 5s, because it's all multiplied, as your coefficients. So deal with those separate from your trig functions. 5 and 5 to the 7th is 5 to the 8th. Over 5 to the 10th is 1 over 5 squared. Okay? Then you get tangent over secant. Now, if they're beside each other, when you have tangents and secants, so this is tangent and this is secant, when they're beside each other, you can't cancel anything. So that's when you think, okay, can I make one thing a u and do all that stuff? But when they're in a quotient, well, that is like sunshine, because that means you have cosines on the bottom. So when you're in a quotient, flip and multiply, and all of a sudden things start canceling. So change tangents into sines over cosines. So tangent to the 8th is sine to the 8th over cosine to the 8th. Secant to the 9th is 1 over cosine to the 9th. If they're divided, you flip, right? Keep, change, flip. If they're divided, you flip it, and things cancel. So when you divide them, cosine, this part, flips over, goes on top, and allows you to cancel. Makes a beautiful u substitution. U, because this is a composition with the derivative, u is sine, derivative is cosine. When you get to u's or thetas or wherever you're at, u's go back to thetas, thetas go back to x's. Remember, this is our theta. So thetas go back to x's, and then everything goes back to your original x over 5 equals secant theta relationship. I'm going to stop and let you guys take a look. Thank you, James, for writing that all out for me while I was walking. While I'm writing this new one up, people can still be looking at the old one to finish up what they need to do. Here we go. The next one, the next warm-up problem is, here we go, antiderivative of x squared over x squared plus 4 to the 2nd power dx. Thank you again, James, for sticking that up there for me. X squared over x squared plus 4 squared dx. The antiderivative of x to the 2nd divided by the quantity x squared plus 4 all squared with respect to x dx. Notice you don't have a square root, but you can still apply a trig substitution because we've got that Pythagorean pattern in there, x squared plus 4, okay? Alrighty, so I'll wonder if you guys have any questions on the one on the left for your warm-up. You can tell me. Otherwise, you guys are working on this last one here in trig sub. You guys are working. Everybody's moving. So you recognize the pattern, and you see it as x squared plus 2 squared, and you say that's x equals 2 secant theta. So dx is 2. I did that wrong. That's a tangent. Slow down, Tina. That's a tangent. Hang on. X is 2 tan theta. Dx is 2 secant squared theta d theta. So this equals, let's see. Am I good so far? Am I good so far? Let's see. Tangent squared theta plus 1 becomes secant squared. Secant squared squared becomes secant to the 4th. 4 squared becomes 16. So we should be doing, everything should be going good there. You guys should be doing good. How are you? Catching it?
Oh, because you just bring it forward.
Figure out where, what I want you to decide. Because that's where we need to practice the one. At the very beginning, you need a lot of shot. So being careful, right? Going through carefully.
I was just like,
how are we?
because I had a 1/2 2, I'm like, no, I put all these in here, when you're integrating your texts, the 4 is from the answer question. Okay.
Max, how are you? Do you see all the spaces so far? What did you do then? Did you cancel things at this point? Garrett, did you cancel things at this point? What did you do at this point? So the 8/16 cancels down to 1/2, right? You guys got a fraction 1/2 in the front? And your secant squares cancel, so you're left with a tangent squared theta over a secant squared theta.
Okay.
And again, we get these things where tangent is sine over cosine. And secant is 1 over cosine. And so that should be saying to our brains, when I have a fraction divide a fraction, I can flip and multiply, right? So you can simplify that complex fraction by flipping and multiplying. That's going to be 1/2 times the integral of sine squared theta over cosine squared theta times flip and multiply cosine squared theta over 1. So that allows us to cancel cosine squareds. And so it looks to me like what we're integrating is just 1/2 sine squared. Is that what you got, Zach? Did you get 1/2 sine squared, or am I missing something? Ha. And Anthony, what do I do with sine squared? What did you think?
I turned it into double
Power reducing formula, the half angle, double angle thing. So 1/2 times the integral of 1/2. It's an even power of sine.
Oh, wait, doesn't work.
uses our power reducing formula. Just moving it up so everybody can see it. So that gives us 1/4. And then 1 minus the cosine of 2 theta d theta, which we can finally integrate. That's going to be 1/4 of theta minus 1/8 of sine 2 theta. Make sure you agree with me and match me. Then you have to go back and do your triangle. So remember, we're distributing the 1/4, right? And then when we take the antiderivative of cosine, we look at the coefficient on that linear interior function. And so we know we have a 1/2 in front. That 1/2 gets multiplied by the 1/4 to give me a 1/8. Tim, are you with me? Yeah. You're sure? So what do I do at sine 2 theta? Because remember, we go back and we make our triangle now, right? Once you get to that point, you have to go back and make your triangle. And the original relationship, hang on, let me go a little bigger. Our original relationship here was x equals 2 tan theta, or x over 2 equals tan theta. So we go back to our triangle, theta equals x over 2, so this side became x squared plus 4. And that's good because that should match my pattern that appears right up here in the beginning, which it does. But sine 2 theta, the problem is I simply have an angle theta, so what do we do there? What'd you guys do there when you got down here to sine 2 theta? Yeah, Gwen. Absolutely. We want to use double angle formula because it's a double angle, but I don't have a double angle in my triangle. I have to think, okay, 2 sine theta, cosine theta. Lots of thinking caps, right? You have to be mindfully present to work a problem like this. You have to be making sure you understand all of the steps. There is no memorization when you're doing trig substitution. It is about critically working your way through the problem and saying, okay, I make my substitution, now what do I do? How do I combine things? How do I simplify things? When I get down here, what do I do with that integral? What pattern speaks to me? And then recognizing we have to go backwards. Sine 2 theta is 2 sine theta, sine theta. So 1/4. Theta is the angle whose tangent is x over 2. I ran out of space, guys. Hang on. I'm not going to go up there. I'm running out of space. So let me go right underneath it. So this equals 1/4. Theta becomes arctan? What? Sure. Okay, Tim. Theta is the angle whose tangent is x over 2. Theta is the angle whose tangent is x over 2. Some people will write it as inverse tangent of x over 2. In other words, take the inverse on both sides. But theta is the angle whose tangent is x over 2. That's the arctan. Minus, we have a 2 in front, so I'll have 1/4 times sine of theta. Sine of theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. And so you guys, if you want, you can cancel it down. You could get a 1/2 coefficient on the whole thing. But I'm just going to stop right there just to show you that's where all the pieces come from. So everybody should be getting 1/4 arctangent x over 2 minus 1/4 x over the square root of x squared plus 4 times 2 over the square root of x squared plus 4. Like I said, we could simplify this down a little more, but I simply want to stop there so we see where all the pieces came from. Who's got questions on that second warm-up, trig substitution, now that our brains are going? Anthony, ask away.
For the theta, wouldn't you be able to use any arc or
Yes, you can. You could use anything. You could say it's the arc sine of x over the square root of x squared. Yes, you can use any arc function. I tend to go back and use the function that has created my triangle or substitution to begin with. Because it's simpler. It's always going to be simpler because it's going to have the x. It's not going to have the square roots in it. So I always like to just go back to the one that I've used. But you can use any of them. That is correct. And we are making all those assumptions about positivity and where our angles are lying, right, to make it all work nice. Ooh, so that brings me up to a question. You're right. You know what? I think I would definitely stick to my original one because arctans are defined in different quadrants than arc cosines are defined when theta is involved. Does that make sense? So I think for the purposes of a trig substitution, I think I would stick to just keeping it what I started with. But yes, it's all the same. They're all on a right triangle would be the same for that theta. Questions, questions, questions?